Good evening. Welcome to University of Maryland, Baltimore County. My name is Paul Mulhern. I'm the marketing manager with the Department of Information Systems. We're here tonight with Phil Feldman, PhD student with Information Systems Human-Centered Computing program. Phil, welcome. Tonight Phil is going to tell us about some of the work he's been doing both as a student in UMBC as well as in the industry. So Phil, I think we're going to start with the exercise video game, correct?
Yes. Yeah, this was a system that we developed at a company, a little startup that we had done back in the early 2000s. The idea was to develop a system that would play off-the-shelf video games and also give you a workout. And we'd spent a lot of time iterating around the concept of how do you provide for what are known as fast twitch games, which are games that people really you have to move very quickly inside of the game environment, but you still need to use large muscles. So what we did was we developed a system that measures force. And so rather than using the controls that you can actually see on the controller, which are sort of for selecting games, instead you press against that entire beam there, and that measures force, and it's electronically adjustable from about a range of 10 pounds of force up to 300 pounds of force. At the beginning, we actually had it developed up to 100, which we all thought was fine, and then we went to a show for fitness. I think it was the Idea show, and this Russian weightlifter comes up and he says, "I will try this," and we gave it to him, and he said, "This is all very good, but it is too easy." So we said, "Okay, come back tomorrow." We changed the code and gave it a 300-pound thing, and he came up, and he really did sound just like Arnold. And so I will try this again, and he tried it, and after 10 minutes of playing around, he was like, "This is very good, I have sweated." And so we thought we really had something, and we went and we had Best of Consumer Electronics show for a couple of years running. Market was pretty good, and then the next generation PS3s and Xbox 360s came out, and the legal issues of having to hook up a peripheral to them became much more complex. So we had to scale back and try a variety of things, and after a while, the economy kind of kicked the company off the edge of the financial cliff. But there was lots of interesting things that came out of this. So this is basically the whole mechanism. The only part that's really active is this part here. Everything else is just bracing to hold you in place, because you can push so hard you can knock yourself around pretty effectively. This is Gran Turismo 3, one of my favorite PlayStation 2 games. And basically, I'm pushing away from me right now to go. If I want to back up, I will pull towards me, sometimes. And if I want to turn, I will push to the left, push to the right. And because it's not just a simple thumb controller, it's now I'm basically in a full crunch at this point. I can hold this for a little while, and I'm really hoping that a turn comes up really soon, because I have it that I'm putting about 150 pounds of force into this right now, which is about as much as I can do and still talk. Coming up over this turn, and so we have the brakes, we turn, accelerate, and so forth and so on.
Phil, how did you get interested in doing this work? And how did this come about?
I had started in surgical simulators and other types of more traditional simulator systems. And they had, there were these very big, expensive systems. And I thought it would be fun to have something that has more interactivity for normal people, that allows them to interact with these reasonably sophisticated systems that we were using. And the question was, how do we do that? And there are these video game systems that were coming online. They were very sophisticated, and it's like, how do we connect to them? How do we make things work? And what would make sense to provide a product that would really get connection? And I remember, I'm a cyclist, and I ride about 10,000 miles a year. And in the winters, there are times that I can't get outside, so I'm sitting there on an exercise bike, or I'm sitting there on a treadmill or an elliptical. And it's just boring beyond words. And I remember looking at the pattern of my sweat dripping on the floor going, there just has to be a better way. And so I cobbled together some stuff at work and put together sort of a preliminary version of this thing. And they said, that's pretty cool, but not exactly what we're interested in. So a couple of people from work and I actually went off, started a company, got the whole venture capital investment funding, went along for 3 years, Did pretty well, got Consumer Electronics Show, Best of Show for like 3 years running. And then the economy collapsed, and that was pretty much it. But what was really interesting with this was the amount of emotional involvement that you get. It's not like you really need to have the steering wheel to feel like you're in the game. It's not like you really need to walk like you're in the game. Just the fact that you're engaged physically makes you feel connected. And the only problem is that you don't know when you hit the walls. You don't know what the terrain feels like. But we have this nice interface device. We were actually able to sell these for like $150 a piece, and that's, you know, after fabrication and everything. So the base technology was things that we could use to provide this low-cost input for really sophisticated actions. What I like to say is that, for example, if I'm playing a first-person shooter, well, these sorts of things allow you to have the level of subtlety and control, for example, with a sniper rifle, that you can compete effectively with a 12-year-old, which is, you know, for an adult, a major achievement. So what I wanted to do after a while was start to take that and move it into a more sophisticated direction. Was it possible to have a way that you could actually not only interact by making something move through the system by pushing against it, but have a way that as you're applying force that you can have a sense of what you're contacting. And that led to this, which is what I started to do on my PhD work. All right, so what we're dealing with here is a system for doing vibrotactile feedback based on force input. So each one of these sensors here, this is a force sensor that's attached to a vibrotactile actuator, and we have 5 of them, 1 for each finger. Actually sits on a mouse platform. And if I push one of these, you'll see the matching finger go. And each finger generates a different tone. And the tone, or the volume of the tone, is proportional to how hard you're pushing on the control. So now I'm pushing very lightly. Now harder. And you can actually feel those cubes move underneath your finger by the volume of the sound changing. So I can take all of these, and I can have this. And again, because each one of these has a different sound to it, I can tell just by listening which one it is. Now, right now I'm just using a synthesizer that runs each one of these vibrotactile feedback systems, but there can be much more sophisticated sounds. So you can have the sound of wood, which is like that, or the sound of glass, which has its own set of reverbs, or plastic. Each one of those has its own sound. That sound can be felt and that sound can be heard, so that you can know what it is that you're touching and how hard you're touching it. So I could have a catalog of fabrics, for example, and have the satin sound mapped to the satin vibration, the polyester sound mapped to the polyester vibration, and actually have the ability to a degree, be able to interact with things like fabric and other materials. One of the more interesting things is in mines, a lot of the decisions on how to insert the charges into the rock is based not on looking at the rock, but actually walking up to it and feeling it. That you actually want to sense, you want to have a sense of where the rock has give and where it's very solid, so that you can have the cleavage planes be correct. And one of the reasons that people still go down into mines rather than having robotic systems is because it's very hard to replace that. But if we can give something that allows people to actually have a sense of touch, even if it's not exactly like what they're dealing with, it's still something where it's like a syntax set of words that you can have that says, this feeling here, these sounds, that's granite. These sounds is dirt, for example.
And thus, I imagine then the applications become well beyond just gaming. correct?
Absolutely, absolutely. Although I think that it would make some of the most interesting games that people have ever played, because now when you want, you've knocked somebody out, you want to see whether or not they still have a pulse. You can actually reach down, touch them, feel the neck, feel the pulse of the neck, and go, oh yeah, that person's still alive? Okay. I'll have to shoot them again. But there's things that you can do once you have that level of interaction with an environment that is pretty remarkable. They have a dexterous hand NIST that I'm in line to use. I think with luck it'll be in about 4 weeks. And it is this amazingly sophisticated dexterous finger. It's got 3 fingers, and it can hold surgical tools, it can hold mechanic tools, but the problem is, how do you know when you're using it whether or not, for example, if you're doing remote surgery, that you're pressing too hard against the skin? Well, with this, I can control this enough that they think, and what they want to demonstrate with is be able to actually take eggs and transfer them between cases. So if it's possible to, using this robot, which has the ability to bend steel, to pick up an egg without breaking it, and to do this with enough sophistication in the action that you can take it from one egg crate, move it over and place it into another egg crate. Well, that opens up a lot. It not only opens up things that are like materials handling, which is what that would be, but let's say that you have a situation where you're trying to defuse a bomb. Well, now you have the ability to actually carefully feel with the wire cutters over the wires and say, yes, I'm on the first wire, the second wire, the third wire, that's the one I want to cut. Or, for example, working on a factory floor. You would never have to, for example, you're in Detroit, the factory nearby has closed down. That's not a showstopper anymore. You actually go down to your basement workstation, log into a factory in California, and go work on Teslas. So it allows for that sort of interaction, sort of that blue-collar telecommuting, as opposed to much more sophisticated actions. One of the things that I worked on in the past, before I actually worked on these things, was the automation of mining equipment. Turns out that mining, no matter how you slice it, is just incredibly dangerous. And the reason that it's really dangerous is because the air explodes. There's coal dust, there's oxygen, any spark at all, and you have a tremendous catastrophic accident. So if you can take systems, and the thing is that when you're interacting with the coal surface, it is a matter of feel. You have to, the interaction, you can't just look at something. You have to be able to basically put your hand against the wall and say, that's where I want to drill. Here's where the fractures are. This is moving easily. This is not. That's where I want to actually place my charges. And you need to have a very sophisticated robotic interaction if you're going to try to do that without humans actually down there. And again, this sort of technology that allows you to have that sense of close contact may provide that.
And you alluded to this with the work with NIST. In addition to that, what do you see as next? What's next for you in your work with this?
Well, the first next thing is the NIST dexterous hand. So the goal here is to, now that we have this, to be able to hook it up to the dexterous hand and actually do studies to see whether or not it is, one, just basically effective. Can we actually do these sorts of tasks? And then to be able to compare it to how somebody would do it if they were there. There are some very interesting things that come out, for example, when you're trying to manipulate heavy objects. People are really good at manipulating light objects like this, but when it comes to doing something heavier like, I don't know, lifting up and moving that, now they're using machines anyway. You know, we have construction machinery and all that, and right now that construction machinery is actually very hazardous to use and damages itself a lot. So if you can treat these sorts of heavy pieces of equipment more like robotic pieces of equipment, now you start to have another way of accessing that. So opportunities with Caterpillar and with the other major construction, Joy is another major manufacturer of construction equipment. Those people are kind of interested in what could happen here. And at this point, mostly the next steps are to test and evaluate how effective an interface it is. Do we connect it to something? Can you do everything entirely by force and vibration? Do you put this on the end of an effector that you can then move and say, I want to move my hands here and now I want to grip? So at that point, the research is kind of wide open. And of course, the entire goal is to make this smaller and easier, because right now, building another prototype takes about 3 months.
Well, great. Well, thank you very much, Phil. We really appreciate your time, and I'm sure we'll look forward to checking in with you again down the road and seeing where this has gone, and I'm sure you'll have invented some other cool stuff by then as well. So thank you very much. Thank you for watching. This is University of Maryland, Baltimore County Television. Thank you and good night.